Hello and welcome to Mrs. Ballard's class. Today we're going to talk about calculus topics 1.10, 1.11, 1.12, and 1.13. So there's a lot of different things going on here, but they all relate to one another, interrelate to one another, so it's good to just talk about them all at one time. We're going to be exploring types of discontinuity, defining continuity at a point, confirming continuity over an interval, and then we're going to be removing discontinuities. And as always, if you need to, pause the video to write things down if I go too fast, or you can rewind as much as and replay it back as much as you want. So our lesson objectives for the day, the essential questions, and there's 4 of them. I did leave you extra space. But again, if you need to pause to write this all down, you can. What are the different types of continuity? How do you find the continuity of a function at a point? How do you find the continuity of a piecewise function algebraically? And how do you find a missing value to make functions continuous? And I know the I can statements kind of seem repetitive compared to the essential questions, but if it's in question form, then it makes it easier for you to answer in your summary. The I can statements are I can identify the different types of discontinuity. I can demonstrate the continuity of a point. I can determine continuity of a piecewise function algebraically, and I can find the missing value to make a function continuous. All right. So I thought that this picture was kind of funny with the no gaps, because that's what basically it is. If it's continuous, it doesn't have any gaps. That's the easiest, most simplistic way to look at it here. So of course, always put your name at the top. Don't miss it, so I know who it is when you turn them in. When I was thinking about continuity and things being discontinuous, it came to mind that we've had some events here in California, even some of them so recently as 2019, where we had things that made roads discontinuous. So we had during Highway 243 up near Idlewild in February 2019, we had a big rainstorm that washed it out. The Bay Bridge in Oakland collapsed in 1989 earthquake, so you can see the gap right there, so it would be continuous. And then the road located in China Lake Navy Base after a 7.1 Ridgecrest earthquake in July 2019. You can see how it used to be a road and then is discontinuous because there's breaks and gaps in it. That one's close to home for me because I grew up in Ridgecrest and I remember having earthquakes all the time. Basically, our tip here is that there's no interruptions whatsoever in the graph. So there's no gaps, there's no holes, there's no way that the graph gets broken up. So I'm going to show you 3 different types of examples of discontinuous functions. And we're going to label them here as we go. So this first one is where f of c is undefined. So in order to be a continuous function, the c value actually has to be defined. So that's our first criteria to meet, is f of c is defined. And basically that means that it exists. So there is an actual solid dot there. The next one is that the limit as x approaches c of f of x does not exist. And here's 2 examples of it not existing. You can see we've got a jump function, and then we've got the limits going to positive and negative infinity. We know both of those don't exist. So in order for a function to be continuous, the limit as x approaches c of f of x must exist. And then finally, right here, the last one, this one's not continuous because the limit as x approaches c of f of x does not equal the function evaluated at that point. So the limit exists, the point exists, but they are not the same thing. So that means that there's still a gap in there. So the third criteria is that the limit as x approaches c of f of x equals the value of the function at that point. Basically, if you'd have to lift up your pencil to draw it, there's no way that that's continuous. Now, you don't always have the picture. Like in this first one, we don't have the picture, but we're still going to be able to tell if it's continuous or not. So we're going to apply the 3 criteria that we just wrote down. So this was an actual free response question in 2011. It was just part of the free response question. They're typically broken into 3 or 4 parts. So, but if you remember this would be some really nice, easy points. So let f of a function be defined by f of x equals, and it's a piecewise function where we've got 1 minus 2 sine x for when x is less than or equal to 0, and e to the negative 4x for when x is greater than 0. We're supposed to show that f is continuous at x equals 0. So the first step of our criteria, and if you want to just number your steps off, you can, is we need to show that, if you want to number them like that, let's see, we could do, oh yeah, they're already numbered 1, 2, 3. Okay, so we have to show that f of c is defined. So we would want to say the c value that they're talking about is this 0. So that's your c value. So we want to find f of 0 and make sure that it exists. So I'm supposed to plug into the top branch there. So 1 minus 2 sine of 0. And we go back to good old unit circle. 0 radians is there. Sine of 0 is 0. So you've got 1 minus 2 times 0, or just 1. So we know that, therefore, f of 0 is defined. All right, then step 2 was we have to show that the limit as x approaches c exists. Since we've got a piecewise function, we're going to do this in 2 branches. So the limit as x approaches 0 from the left, we're going to use the top branch. So we've got of 1 minus 2 sine x, and we're going to plug our 0 in there. 0, which we already calculated that. We know that it's 1. And then we're going to do the limit of the right branch. So we're using the bottom function, e to the negative 4x. So it gives e to the negative 4 times 0, or e to the 0, which also happens to be 1. So therefore, the limit as f of x, or of f of x, exists. And then step 3 is to show that the limit does in fact equal the value at the point, and we've already shown that because this would be the limit and this would be the value at the point, but we need to actually state it and write it down to get your full point. So the limit as x approaches 0 of f of x equals 1, which equals f of 0. And you can write that. That's a fancy math sentence way of writing that. And then I would probably conclude, therefore, f of x is continuous at x equals 1. No, sorry, not x equals 1, x equals 0. So I'm going to tell you that there's 2 different types of categories, and we may or may not have gone over this in pre-calc or algebra 2 trig, that you can categorize these functions into. Either you're going to categorize discontinuities into removable or non-removable discontinuities. So I'm going to give you a couple of minutes, and I want you to see if you can kind of analyze that graph. Just take a minute and see how many words you think you can get in there. I already kind of hinted at what the 2 types were. So this would be a good time to pause the video, and then I will go through it here in a few minutes. So we told you there's 2 different types of discontinuity. There is non-removable, and I would put non-removable with a factor, a denominator that will not cancel away. And then there's removable. So our graphical descriptions is, and we've been doing this for a little while and we really haven't talked about it a whole lot. Sometimes we get to our limits and we have a limit that comes up like this, and we're able to cancel something. When we're able to cancel something, that becomes a hole in the graph. So we know that that is a hole when the denominator will factor away. If I had the opposite situation, 3x minus 2. I still have a hole, but then whatever's left in the denominator. What is left in the denominator is the vertical asymptote. You have to set it equal to 0. So in this case, the vertical asymptote would have been x equals -3. Okay, so the two things that would go here would be a vertical asymptote. And then the other time that we get things that won't cancel away is when we have a jump type of function. That's also discontinuous. All right, so let's see if we can get some of this off the graph. So the graph below is f of x. Determine all x values where f is not continuous and classify each as removable or non-removable. So I'm going to go removable, or I'm going to make two categories, non-removable and removable. And we're going to always add x equals, add x equals. Okay, so let's start. I'm going to just start from the left. And anytime I'd have to pick up my pencil, I know I've got one. So right there, I'm discontinuous, but I could fill in the dot, right? Which means it would be, it is possible to get that dot filled in under the right circumstances. So I know that that one's removable. Holes are always removable. Okay, I'm going to keep going. I have another one right here, and that's another hole. So I'm just going to make a list, x equals 1. I'm going to keep going, and then right here I've got a jump going on, and a jump is not something that we can remove. And that's in our chart there. So we've got x equals 4. And then I'm going to keep going. Oh, and I've got this asymptote. I can't remove that. So I know also at x equals 5. So now we're going to do one without a graph. So we're doing the analytical approach now. Consider h of x equals x squared plus 3x minus 10 over x squared plus 2x minus 8. We're supposed to list all the x values where h of x is not continuous and classify each type of discontinuity. And then we're going to write the intervals over which the function h of x is continuous. So the first thing I need to do is I need to factor this thing. So if I'm going to do my good old magic x, I need two numbers that multiply to -10 and add to 3. So that would be 5 and 2. It looks like 2 has to be negative. So x plus 5 times x minus 2. And then I need two numbers that multiply to -8 and add to 2. So that'd be 4 and 2. Looks like 2 is negative. So x plus 4 times x minus 2. All right, we're going to cancel something. So when I cancel, remember when we do the canceling in the vertical asymptote, you always set it equal to 0. So we know that at x equals, 2, x equals 2, I have a hole, okay, which is removable. So we could say that there is a removable discontinuity at x equals 2. And if you want to put in parentheses to remind yourself that it's a hole, that's not a bad idea, okay? All right, now we still have something left in the denominator, and we have something left in the denominator. We set that equal to 0. So we got x equals -4, and we know that that is our vertical asymptote. So we know and that's a non-removable discontinuity. So non-removable discontinuity at x equals -4. And if you want to, in parentheses, put that it's a vertical asymptote to remind yourself, you can. Now we haven't done the last thing. Look at the end, like at the last sentence. Write the intervals over which the function h of x is continuous. Well, we know it's continuous everywhere except at these two gaps. So I am going to write some intervals that, or where it's continuous. So I'm going to say that it's continuous on, I'm going to start at -infinity, and then I'm going to go to the smaller number, which is -4. And then I'm going to pick it up again at -4, and I'm going to go till I hit 2 because there's a hole at 2. Then I'm going to pick it up at 2 and go all the way to infinity, and those are the intervals that it's continuous on. There's another way that we could write that. We could also write that it's continuous for all real numbers except x equals 2 and -4. All right, so now we've got a piecewise defined function for g of x. Determine all x values where g of x is discontinuous and classify each as removable or non-removable. All right, so we are going to have to test the right and the left-hand limits. It's the only way to do this. So notice that this and this go together. So I'm going to do the left-hand limit and the right-hand limit. So the limit as g of x. Ugh, what am I doing? Limit as x approaches -2, whatever that break is right there, that's our value. So -2 of 2x minus 1. So that'd be 2 times 2 minus 1, which is 4 minus 1, which is 3. And then we have the limit as x approaches, I'm sorry, I should have put left on that. -2 from the right, which I'm going to use that bottom, the next branch, x squared minus 9. I'm going to put in the 2, so I've got 4 minus 9, which equals -5. So it definitely looks like that part is discontinuous there. And that would be non-removable. So you might want to just write that there. We'll do a official later. Okay. All right, we're going to do the next one, and that it looks like it's at 1. So the limit as x approaches 1 from the left. So now this is the left side of this branch. So x squared minus 9 equals 1 squared is 1 minus 9 is 8. And then we're going to limit as x approaches 1 from the right. So now the 1 from the right is this branch right here, 3x plus 2. So we've got 3 times 1 plus 2 equals 3 times 1 is 1, or sorry, 3 plus 2 is 5. So it looks like we've got another non-removable here. And let's look at, now I have to do this last branch here. So 3 and 4x minus 1. So the limit as x approaches 3. We're going to do this branch here first, 3x plus 2. And so we've got 3 times 3 plus 2, which is 9 plus 2, which is 11. Sorry, that I should have put from the left. And then the limit as x approaches 3 from the right. So I'm going to use the bottom branch, 4x minus 1, which is 4 times 3 minus 1. So that's 12 minus 1, which is 11. So finally, this here is continuous. And then typically with piecewise, it always is a non-removable because it's some kind of a jump function. So we would want to make a statement about the continuity. Oh, we were supposed to classify each. Okay, so we're gonna say something like g of x has non-removable discontinuities at x equals -2 and 1. And is continuous, because we have to show where it's continuous, for all real numbers except x equals -2 and 1. All right, now AP loves this kind of problem. You see them pop up all over the place. So now what we're going to do is we're going to find the constant a such that the function is continuous on the entire real line. So basically what you do is if it's continuous, we know that you can evaluate both of these. Oh, you can plug them in, but not quite. We know that their limits should be equal when those x values are plugged in. So I'm going to do the limit as x approaches 0 of 4 sine x over x, and that should equal the limit as x approaches 0 of a minus 2x. All right, well, I know when I'm approaching 0 that this is one of our special trig limits. It's 1, and 4 times 1 is 4. And then this only goes in for the x value, so we've got that a minus 2 times 0, so that means that 4 equals a. So I know that if I put a 4 in for that a right there, that would make the function continuous. All right, we're going to try one more of these continuous ones. This one's a little bit more of a bear because I've got 3 branches, which means I'm going to have more equations that I have to deal with. And we're going to look at the right and the left side here to make sure, or to find the continuity here, left and right. All right, so I'm going to start with 2. So the limit as x approaches my limits have to be the same. Okay, yeah, so the limit as x approaches 2 from the left of x squared minus 4 over x minus 2. So I know that I'm going to need to factor this first because I know I can't just plug a 2 in there. So limit as x approaches 2 from the left of x plus 2, x minus 2 over x minus 2. I know those cancel. So I have the limit as x approaches 2 from the left of x plus 2. I plug in a 2, so I get 2 plus 2 equals 4. All right, then I'm going to do the limit from the right, which is this one here. So the limit as x approaches 2 from the right of ax squared plus bx plus 3. And I'm taking a similar approach, just a little bit different on this one. So now I'm going to go ahead and plug my 2 in there for the x's. So I get a times 2 squared plus b times 2 plus 3. That's b, not 4. All right, now I'm going to simplify that a little bit, which gives me 4a plus 2b plus 3. Now I'm going to do the same thing, but I'm going to do the 3's now. So I got to do this one with the 3. So I've got the limit as x approaches 3 from the left of ax squared plus bx plus 3, which gives me a times 3 squared plus b times 3 plus 3. If I simplify that, I get 9a plus 3b plus 3. Okay, and then one more. I'm going to do this branch from the right. So the limit as x approaches 3 from the right of 2x minus a plus b. I'm going to go ahead and substitute in for my x. So I get 2 times 3 minus a plus b, which gives me 6 minus a plus b. So now the question is, I still have all of this stuff. I got to figure out what these are equal to here. So I know that the right hand and the left hand limits have to be equal in order for it to be continuous. And maybe if I set them equal to each other, I can come up with some equations where I can use them to solve for A and B. So if I'm going to start with these two equations and set them equal to each other, so 4a plus 2b plus 3 equals 4. And then I'm going to set these two equations equal to each other. So that is 9a plus 3b plus 3 equals 6 minus a plus b. Now, if you remember back to algebra, we know that we have these things called systems of equations. And basically that's what we just did, was we made a systems of equations. I'm going to do some simplifying on it a little bit. So I'm going to do kind of color-coded. I'm going to move this to the other side. So I've got 4a plus 2b equals, I'm going to subtract the 3, so it gives me 1. And then on this one here, I'm going to do some combining of like terms. I'm going to move this a to the other side, so 9a plus a is 10a. And then I'm going to move this b to the other side, so 3b minus b is 2b. I'm going to choose to move the 3 to the right. So I'm doing 6 minus 3, which is 3. And then I messed something up. Oh, I was adding A over here, or adding B over here. Something went wrong somewhere. Plus B. No, I should be subtracting. Did I write this down wrong? It should have been a negative 3B. And I wrote it wrong somewhere. No, not there. Yes, there. Did I type it wrong originally? No. Sorry, there's something wrong with it. I want to make sure I don't do it wrong. I think there's a typo in the problem. It doesn't affect much. It's just going to affect a couple of our signs. So right here, there's a typo in the problem. It should have been a negative sign, which means I'll have it fixed on your paper probably, but I got to fix it here now, which means that this is going to be a negative, which means this is going to be a negative, which means this is going to be a negative, and means that this is going to be a negative. And it's going to mean that then that this is a negative. Okay, then it also means that this one gets affected, so that's negative, that's negative, that's negative, and that's negative. So when I bring the B over, instead of it being positive, or it's going to be negative 3B and negative B is going to be negative 4B. All right, that's looking a little bit better now. All right, so we've got what looks like a traditional systems of equations set up there. We can use either substitution or elimination. I'd probably use elimination. I'm gonna have to multiply this one by 2 to eliminate. So I can get actually negative 2, so I can get these to cross out. So I would have negative 8A plus 4B equals negative 2. Remember, don't forget to distribute over the whole thing. And then this one, I'm just gonna write down the way it looks. And then I'm going to go ahead and use the elimination method and add them up. So negative 8A and 10A is 2A. The B's go away. And negative 2 and 3 is 1. So A is equal to 1/2. And then I have to substitute back in somewhere to get B. So I'm going to just go ahead and go into the green one. So 4 times 1/2 minus 2B equals 1. These guys cancel, so it's 2 minus 2B equals 1. We move the 2 to the other side by subtracting. So 1 minus 2 is negative 2. I'm going to divide. 1 minus 2 is not negative 2. It would be negative 1. I'm going to divide by negative 2. So B is going to be equal to 1/2. And that concludes our lesson for the day.